All right, guys, now we're going to do some application problems with differential equations. So you're going to have to write your own differential equation here, then solve it. There's going to be an extra constant in here, as you'll see in a second. And then we're going to use that equation to answer some questions. So very similar to what you might see on a free response question here. All right, so rate of change, so derivative of the number of bacteria, y, in a culture is directly proportional to the number of bacteria. All right, so first step is to write the equation. So rate of change of y is dy over dt. And then if it's directly proportional, then that's going to be k times whatever it's proportional to. And it's proportional to the number of bacteria, and that's y. So it's equal to k times 1. All right, so part A is find the formula for the number of bacteria at time t. So we're going to have to solve this equation. So we're going to separate our variables. So we're dividing by y, 1 over y dy, and we're multiplying by dt, so k times dt. All right, we're going to integrate this on both sides. Since we have a y to the first power in the denominator, that's going to become a natural log of the absolute value of y. And then over here, we just have a constant, so we're just going to tack on the variable there, kt, and then we're going to add our constant of integration as well. All right, one thing that you might have noticed reading through this problem is that there are two different initial conditions. So we have the t equals 0, y equals 2,000, and t equals 3, y equals 10,000. And the reason we need two of them is because there are two different constants here. All right, so we're going to start out with the t equals 0, and we're going to go ahead and plug that in here. So we get natural log of 2,000 is equal to 0 plus c, or just c. So c is natural log of 2,000. All right, so I'm going to rewrite my equation here. Natural log, absolute value of y, is equal to kt plus natural log of 2,000. All right, so now we want to find k. Again, you could do this later on in the problem, but I like to go ahead and find it now, then we can solve for y at the end. So we're going to plug in 3 for t and 10,000 for y. So natural log of 10,000 is equal to 3k plus natural log of 2,000. All right, so I'm going to subtract this natural log over here. So we get the natural log of 10,000 minus the natural log of 2,000 is equal to 3k. This is a log property. We can combine these into a single log by dividing the arguments, 10,000 over 2,000. And then that simplifies to 5. And then we can divide by 3. So natural log of 5 over 3 is equal to k. All right, we are eventually going to use a calculator on this problem to find some of our answers, but we don't want to do that now because we want our equation to be as exact as possible before we start rounding stuff off. So I'm just going to leave it like this. You could also treat this as a 1/3 in front and move it up and make it an exponent, which would make this a cube root of 5. So if you want to write it like that instead, natural log of the cube root of 5, that would probably be okay as well. All right, so let's plug this in right here. All right, so we have the natural log of the absolute value of y is equal to the natural log of 5 over 3 times t plus the natural log of 2,000. All right, so now we're trying to get y by itself. So we're going to exponentiate both sides. And again, remember on this side, we're getting both of those terms as the exponent there. So we end up with the absolute value of y is equal to e to the natural log of 5 over 3 times t times e to the natural log of 2,000. All right, so this e and natural log will cancel, so that gives us 2,000. E to the natural log of 5 over 3 times t is equal to the absolute value of y. And then we can drop our absolute value, and remember that creates a plus or minus, but we know which one it's going to be based on our initial condition. Our initial conditions are positive numbers, So we want a positive 2,000 here. So 2,000 e to the natural log of 5 over 3 times t. All right, and that would be the answer to part A. All right, B and C are just using that equation to answer some questions. So part B is how many bacteria were present at t equals 5. Round to the nearest whole number of bacteria. All right, so we're just plugging in 5 for t. So y equals e to the natural log of 5 over 3 times 5. And I forgot my 2,000 in front. So let's try that all again. Y equals 2,000 times e to the natural log of 5 over 3 times 5. All right, and we just plug that into the calculator and we will get an approximate answer. So let's do that real quick. All right, 2,000 times e to the natural log of 5, parentheses, divided by 3 times 5. And with the CAS, you have to hit Control Enter. I always forget to do that. All right, so 29,240 bacteria. All right, and always with these problems, just kind of take a beat and make sure that your answer actually makes sense. If it was 10,000 at t equals 3, then it should be bigger. It's an exponential function, so it's getting bigger. And 29,000 seems like a reasonable answer if we're growing exponentially at a certain rate. So seems like a reasonable answer there. All right, part C, we have to find the time when there were 35,000 bacteria. So that's plugging in 35,000 for y. So 35,000 is equal to 2,000 e to the natural log of 5 over 3 times t. All right, so we're going to divide by 2,000 on both sides. So we end up with 35 over 2 is equal to e to the natural log of 5 over 3 times t. Then we're going to log both sides to get rid of the e. All right, and so we end up with natural log of 35 over 2 equals natural log of 5 over 3 times t. And then we just need to multiply by the reciprocal here to cancel that out. So we're going to multiply by 3 over the natural log of 5. All right, and then we're just going to plug that into our calculator as well. So let's do that. All right, 3 over natural log of 5 times natural log of 35 over 2. And let's hit Control Enter this time. And there we go. So 5.335. It didn't mention anything about rounding here, so we're going to go with our 3 decimal places as our default. So t equals 5.335, and it looks like we're in hours here. So hours. Okay, and just like the last part, I'm going to make sure that that answer makes sense. If at t equals 5, it was 29,000, then 35,000 should be a little bit bigger than 5. So 5.335 seems like a reasonable answer there. All right, flip it over on the back and give the next one a try on your own, and then unpause the video and see how you did. All right, I'm gonna have to move a little faster here so I can get this all in. So letter A, we have dn over dt is equal to k times 1200 minus n as our differential equation. Separate and solve, so we're going to divide by 1200 minus n dn and multiply our dt over here. Then we're going to integrate. Okay, once again with an n to the first power we get a natural log of the absolute value of 1200 minus n. But since it was a negative n, we're going to end up with an extra negative constant in front of that. And then over here we get kt plus c. All right, let's plug in our initial conditions and figure out what our constants are. So negative natural log of 900, plugging in 300, is equal to c. All right, so we'll rewrite our equation here. Negative natural log, absolute value of 1200 minus n is equal to kt minus natural log of 900. All right, and then we're going to plug in our other initial condition, which is 4 and 600. So we get negative natural log of 800. No, that's not right. 600. 1200 minus 600 is 600. Is equal to 4k minus natural log of 900. All right, so we add our natural log over here. We end up natural log of 900 minus natural log of 600 is equal to 4k. Those logs combine together into 900 divided by 600, which reduces down to 3 over 2. And then we divide by 4. So natural log of 3/2 over 4 is equal to k. All right, let's plug those back in over here. So negative natural log of 1200 minus n is equal to natural log of 3/2 over 4 times t minus natural log of 900. All right, now we need to get our n by itself. So we're going to multiply everything by -1 first. And then we're going to exponentiate to get rid of our log. We can drop our absolute value bars. Once again, we have positive initial conditions, so we just have a positive 900 in front. And then we just get our n by itself from here. So we end up with n equals 1200 minus 900 e to the negative natural log of 3/2 over 4 times t. And that answers part A. All right, part B. T equals 7. So we have n equals 1200 minus 900 e to the negative natural log of 3/2 over 4 times 7. Round your answer to the nearest whole number of bears. So we just plug this in our calculator from here. All right, 1200 minus 900 e to the negative natural log 3/2 over 4 times 7. All right, looks like we have 757. All right, in part C, we're going to find the time when there were 900 bears. So I'm going to do that down here. So we get 900 equals 1200 minus 900 e to the negative natural log of 3/2 over 4 times t, and we're solving for t. All right, so we need to subtract 1200, so negative 300 equals negative 900 e to the negative natural log of 3/2 over 4 times t. Divide by negative 900, and we get 1/3. We're going to take the log of both sides, so log of 1/3 is equal to negative natural log of 3/2 over 4 times t. And then we just need to multiply both sides by the reciprocal. On both sides. Alright, I'm out of time on my video, so you can imagine plugging that in the calculator and getting an answer. And that answer is 10.838. See you next time.